start recording. Let me share my screen. Okay. All right, so let me just remind you quickly what we did last time. So remember, we defined the notion of sine and cosine using the unit circle. So basically, every angle will give you a point on the unit circle by looking at the terminal side of the angle, and you're writing a standard position. And the point of intersection of the terminal side and the unit circle as a unique point that we're talking about. And then this point is going to have coordinates x and y. The x value of the point is defined to be as cosine of the angle, and the y value of the point is what we call sine of the angle. So using this idea and playing a little bit with geometry, we actually figured out the values of sine and cosine for the three special angles, because these are important. They're going to be popping up a lot. So we did that last time. Let me just summarize the results in a little table. Okay. So this is just, I'm continuing the notes from last time. Just put the angle, and then here we're going to have the sine, and then let us write cosine. Remember that we actually have a little bigger table because we also know all the quadrantal angles. But I will just do this for the special angles now. So sine, well, there will be fractions. So and then cosine. And then the special angles are 30 degrees, which in radians is pi over 6. Then we have 45 degrees, which in radians is pi over 4. And then we have 60 degrees, which in radians is pi over 3. Okay, so last time we saw that the sine of 30 degrees, it was equal to 1/2, okay? And then the cosine of 30 degrees, it was square root of 3 over 2. So once again, that was something that we figured out last time, but, you know, doing a little bit of geometry. Then at 45 degrees, that was the case of the isosceles triangle, so that one was very easy to figure out. So the sine was square root of 2 over 2. The cosine was also square root of 2 over 2. Okay, and finally 60 is the information that we have above, which is, if you notice, is the same values of 30, but they are flipped. Okay, so the other way around. The sine of 30 is the same thing as the cosine of 60, and then the cosine of 30 is the same thing as the sine of 60. So sine of 60 is square root of 3 over 2, cosine of 60 is 1/2. We're going to look at these properties later. 30 and 60, they have the property that the sum equals 90 degrees. So those angles are called complementary angles. And there is a theorem that says that cofunctions of complementary angles are equal. Okay? So the sine and cosine, they are cofunctions. That's why it's called cosine. And so the sine of one is going to be the cosine of the other one, and the other way around. The cosine of one, the sine of the other. So 30 and 60 are complementary, so that's why they enjoy this property. 45 is complementary to itself because the sum is 90, and so sine and cosine are equal. Okay. Anyways, we'll talk about that later when we talk about right triangle trigonometry. Okay, so this is a summary of what we did last time. Now, you know, what sort of questions you're gonna be asked? Well, first of all, you are expected to know these values. Okay. But then the question is, knowing these values, could you use this knowledge to actually figure out other values for other angles? And the answer is yes, and we're going to come back to the idea of reference angles. Okay, so the whole point here is in figuring out knowing what's the relationship between the sine and cosine of an angle and its. Then we're going to be able to do more examples. So let me remind you of the notion of reference angle. So recall, so given an angle, how did we define the reference angle? It was the acute angle formed between the terminal side of your angle and the x-axis. Okay, so given an angle theta, then its reference angle, let's call it alpha, is the acute angle formed by the terminal side of theta and the x-axis. The terminal side of theta and the x-axis. And as you know, each quadrant has a corresponding reduction formula that relates theta and alpha. So a reference angle, and its reference angle. So a natural question now arises, given an angle theta, what's the relationship between the sine of theta and the sine of alpha, where alpha is the reference angle of theta, specified above, and then similarly, what's the relationship between cosine and cosine of alpha? Okay, this is what we would like to explore now. So, is there a relationship whatsoever? Maybe there's no relationship at all. Okay, so is there a relationship between sine and cosine of theta and its reference angle? Between sine, cosine of theta and its reference angle. Okay, so this is what we're trying to do right now. All right, so let's see. First, as you know, depending on the quadrant that theta lies, is the relationship that we have with reference angle in terms of formula, because the reduction formula. So we're going to study this by cases. Okay. So for example, if theta is already in quadrant 1, what can we say? So if theta is in quadrant 1, what do we know about theta and alpha? Anybody? If the angle theta is already in quadrant 1, what do we know about theta and alpha? So what would be what's the reference angle of an angle in quadrant 1? Let's see, 35. What's the reference angle of 35 degrees? Can anybody tell me? No. Look at the definition. Look at the definition. What's the definition of reference angle? Is the acute angle formed by the terminal side of theta and the x-axis. We did it at the beginning. Finding reference angles. So you have an angle of 35 already. I mean, what's the reference angle of this guy? What's the angle between the terminal side and the x-axis? It's just itself. Do you understand this? The angle is in quadrant 1 is equal to its own reference angle. Okay, so this is not really interesting to consider. All right, so if theta is in quadrant 1, then theta is the same thing as alpha. They are equal to each other. Okay, the reference angle is itself. So what can we say about the values of sine and cosine? In this case, are they the same or are they different? If the two angles are the same, so they are equal, right? And so the values of sine and cosine are the same. So here we get that sine and cosines are equal to each other because, well, the two angles are the same, but it's not really interesting. So let's see what happens then in the other cases. So there are 3 more cases to consider, quadrant 2, 3, and 4. So there are 3 cases now. So 3 cases. Case number 1, let's look at theta in quadrant 2. And let's draw a little picture just to understand what's going on. So if theta is in quadrant 2, then it's going to look like this. So we have here the terminal side, and this is theta. Okay, it's an angle in quadrant 2. And then let's see what we can do. So as usual, we're gonna draw our unit circle. make it look like a circle. Okay, more or less. Okay, imagine that that's a circle with center at 0, 0. Okay, so we have our unit circle. So this is 1, 1, -1, -1. And then we have theta over there. And then this guy right here is alpha. Okay, so I want you to look at the following picture. So if this is alpha, then I'm going to draw another picture with alpha over here. So let's draw another picture with alpha here. Circle, and then we have alpha. So this right here is our alpha. Okay, so I'm gonna call this point right here, let's call it P. This is the point corresponding to theta, and therefore when we draw alpha, there is a point corresponding to it. So let's call it Q. Okay, the point here, we're gonna call it Q, and then P has some coordinates, x and y. So I'm gonna call this x theta and y theta, and as you know, x theta is gonna be equal to cosine of theta, and y theta represents the sine of theta. So the x value of P is the cosine, the y value of P is the sine. Now similarly, Q here is gonna have coordinates x comma y. I'm gonna call it x alpha, y alpha, and as you know, the x alpha represents the cosine of alpha and y represents the sine of alpha. So really, the question that we are trying to answer here is there a relationship between the x's of these points? Is there a relationship between the y's of these points? Do you guys understand the question? So to answer, to figure out what's the relationship between, let's say cosine. If you want to know what's the relationship between cosine of alpha and cosine of theta, that's the same thing as looking at this picture and trying to decide what's the relationship between the x values of these points, the x of P and the x of Q. Remember, this is what cosine is the x value on the point corresponding to the unit circle. You understand this? And same thing, if you want to figure out the relationship between the y, between the sine of these angles, relationship between sine of alpha and sine of theta, what we should really look for is relationship between the y's of these points, y theta versus y alpha. Okay, so let's do this. So to do this, we're going to do a little bit of geometry as usual. So let's drop a perpendicular down here. This is a 90 degrees. And then I want you to focus on this yellow triangle that we have here. Okay? Now I'm going to do the same thing on the other picture. Drop a perpendicular. This is 90 degrees. And then let's focus on this yellow triangle over here. So notice that I color both triangles yellow. I claim that these two triangles are equal. And you guys see why these two triangles are equal. For example, they have both the same angle alpha, angle of 90 degrees. So what does that mean about the third angle? This guy right here is going to be the same as this one. Can everybody see that? Because the sum of interior angles is 180. Moreover, the hypotenuse of this triangle right here is 1 because that's the radius. The hypotenuse here is also 1 because that's the radius of the unit circle. So there is a criterion, if you remember, which is called the side angle criterion. That says that if you have two triangles with the same side and the same adjacent angles equal to each other, then the two triangles are equal. Okay? So you have two triangles and they have the same side here, and then if this angle is the same as this one and this angle is the same as the other one, then the two triangles are going to be equal to each other. Okay? So this is the angle side angle criterion. There are three criteria for equality: angle, side angle, side angle, side. So That's two sides and the angle in between. If this happens, then the two triangles are going to be equal to each other, or a side, meaning, if the three sides are equal, then the triangles are going to be equal to each other as well. You remember these criterions of equality? So Sarah, you learned this back in high school. When you study geometry at some point, you learned this. So this is previous knowledge. These are the criterions for equality of triangles. Do you remember this? Studying this? Well, I mean, we need this to understand what we're doing. I'm not going to be asking you to show the two triangles, to prove that two triangles are equal. But if you want to understand what we're doing, you need to know this. Okay. All right, so that means that these two triangles that we draw here, they are equal to each other because of the angle side angle criterion. Okay. All right. So let me write that down. And so the two triangles above, the ones that are shaded in yellow, are equal by the angle side angle criterion. Okay, so in particular, if the two triangles are equal, that means that the corresponding sides are equal to each other. So let's see. On the left, the side corresponding. Let's see. First of all, this guy right here. This guy right here. This is x theta, right? And then this opposite side here. What is it? That's the one that is, opposing alpha. That's gonna be exactly y theta. Can everybody see this? You understand this? The coordinates of the point P tells you the length of both of those sides. X theta, and then the y value is y theta. Is this okay? Right? Now let's go to the other triangle. So what do we have here? So along the x-axis right here, so this is gonna be x alpha, and then this opposite side here is gonna be y alpha. Okay? So by the equality of triangle, then what can we deduce? So from here it follows that y theta is gonna be the same as the y alpha. And moreover, what can we say about the x's? Well, if you see the two x's, they have to be equal to each other, but one is positive and the other one is negative. So in absolute value, they are equal, right? In other words, x theta equals minus x alpha. Notice that x alpha is positive, but x theta is negative because it's going towards the negative part of the x-axis, but they have the same length, so the absolute value is the same, right? So from here, what do we deduce? Well, in quadrant 2, the sine of theta, which is given by y theta, is the same as the sine of alpha, and the cosine of theta, which is given by x theta, is the same as minus cosine of alpha. You guys okay with this? Did you understand this? Okay, so that's what we get in quadrant 2. So what's the relationship between sine and cosine of an angle and its reference angle? Well, they are either equal, in absolute value they are the same. It's just that they may differ by a sign. One could be positive, the other one negative, but in absolute value, the two values are the same. Sine of theta is sine of alpha, cosine of theta is minus cosine of alpha. All right, so let's do something similar now, quadrant 3. I'm gonna leave quadrant 4 for you as a homework, but I'm just gonna list the result for quadrant 2, or quadrant 4. The quadrant 4 is very similar to what we did here in quadrant 2. So let's look at quadrant 3, which is the other interesting one. So if theta is in quadrant 3, let's see, what will be the picture? So we have our unit circle. Just draw it there. Then do my x and y. So x 3 here. Okay, x and y. And then let's say that we have an angle in quadrant 3, so the terminal side is going to be somewhere in here. Let's say this is theta, so I don't mess up the picture. I'm going to write it like this. Let's say this is theta, and therefore, it gives me a point on the unit circle. Let's call it P. This is 1, 1, negative 1, negative 1. As usual, this point has coordinates x theta, comma y theta, representing the sine and the cosine of theta. And in here we have our angle alpha. Okay, so if I go ahead and if I extend this line to the other side, can anybody tell me what is this angle? Quadrant 1 that I'm writing is also alpha. Very good, because they are vertical angles. They are opposed. They share the same vertex, so they are also equal. Okay, so that's the reference angle. That's the quadrant 1 version. So instead of drawing two pictures, I'm just drawing the two pictures in one. Okay, if you want. All right. So as usual, I'm gonna look at this triangle right here, and then we're gonna look at the corresponding triangle over here. And once again, here we get a point. Let's call it Q. That has x alpha, comma y alpha. Those are sine and cosine, or rather cosine and the sine of alpha, respectively. And then we have this triangle. Once again, they both share alpha. They have a 90-degree angle. Therefore, this angle right here is the same as the other one. So the three angles are equal to each other. And moreover, because this is the radius, the two triangles are again the same. So two triangles are equal by same thing, angle, side, angle criteria. Guys, okay so far? Right? So because the triangles are equal, then we can draw some conclusions about the size of the triangle. In particular, this will tell you something about the coordinates of the point. So let's see, who can tell me what's the relationship between y theta and y alpha, and what's the relationship between x theta and x alpha? So let's see, y theta. What we conclude then? How does y theta relate with y alpha? Is there any relationship whatsoever? So y theta is minus y alpha. Very good. So, okay, Maria, so instead of delta, we say theta. So, I think actually there is that's how we would write it in English. Okay, theta. Delta, this is lowercase delta in Greek, and this is capital letter delta. That's different. Theta, this is the Greek symbol. Okay, good. So it's minus. No, it's okay. I mean, we're not doing Greek. It's just that, in mathematics, we like to use a lot of Greek letters just because, a lot of these ideas, they are due to the Greeks, just respecting their legacy. That's why I understand. Yeah. So, for example, in calculus, you will be introduced to this friend. This is epsilon. It looks like an E. And in mathematics, epsilon stands for a very tiny little positive number. 0.000000000, and so you will be meeting more Greek little letters. Okay, so y theta is the same thing as minus y alpha. Very good. And how about x theta? What's the relationship between x theta and x alpha? Anybody? How does x theta corresponds to x alpha? Very good. It's going to be minus x alpha. So therefore, this time, what do we obtain? So this time we have that the sine of theta, which is given by the y of theta and the cosine of theta, which is given by the x. What are they equal to? This is equal to minus sine of alpha, and this is equal to minus cosine of alpha. Okay? So again, just like before, there is a close relationship between the sine and the cosine of the two angles. They're basically the same, it's just that sometimes they will differ by a sign. Okay? Like for example, in quadrant 2, the signs were equal, but then cosine, they had opposite sign, was positive and one negative. Here, the sine of theta is minus sine of alpha, cosine of theta is minus cosine of alpha. But for example, we could summarize both of these in the following condition. So absolute value of the sine of theta is the same as the absolute value of the sine of alpha. Absolute value of cosine of theta is the same as absolute value of cosine of alpha. Basically, I'm putting absolute value to remove the plus of the positive or the negative. Whatever it is, when you do absolute value, they are always the same. The same thing is happening here, right? Absolute value of sine matches with absolute value sine of alpha. Absolute value of cosine matches with absolute value of cosine of alpha, because the absolute value removes the negative. Okay? Any questions about this observation so far? Okay, and by the way, notice that really we should not be even putting absolute value around sine and cosine of alpha, because alpha by definition is always an angle in quadrant 1. And what do we know about angles in quadrant 1? The sine is positive and the cosine is positive. In other words, what could be positive or negative is the value of the sine or cosine of theta, depending on the quadrant that theta is. But alpha is always positive because it's an acute angle. In quadrant 1, the sine and cosine are both positive, as we discussed last time. Okay? So, in other words, if you want to figure out from these formulas which one should you make negative, ask yourself in what quadrant is theta. For example, when theta is in quadrant 2, as you know, an angle in quadrant 2, the sine is positive, so that's why sine of theta is the same as sine of alpha. But the cosine is negative, so that's why cosine of theta is minus cosine of alpha. In quadrant 3, both sine and cosines are negative, and that's why you see in the formula both of them being negative. Who can tell me what would be then the result in quadrant 4, following this idea? So case 3, that's quadrant 4. Okay. And we do this in a similar way. So similarly, what do we obtain? So who can tell me? Let's see. So think about it. What do you know about quadrant 4? Let's see, sine of theta. So if theta is in quadrant 4, what are you expecting? Are you expecting a positive or a negative value for the sine of theta? And then same question for cosine. Let's see, in quadrant 4, what do we know about sine? Is it positive or negative? What do we know about sine in quadrant 4? Are you sure, honey? So, okay, so let's see. Think about it, guys. Draw a picture in your mind. You are in quadrant 4. If your point is on quadrant 4, remember the x value of the point, what does it give you? Does it give you cosine or does it give you sine? So a point in quadrant 4, what does it have positive? X or y? It has a point in quadrant 4, so you have quadrant 4, you have a point here. The x is positive, the y is negative. Yes? So in quadrant 4, cosine is positive, and the sine, which is given by the y, is negative. And you could choose to memorize these things, but I wouldn't memorize it. Just think about it. Look at what the point is, and then you'll be able to know exactly the sign. If you remember, of course, that cosine is x and sine is y. Okay? All right, so sine of theta then, it has to be negative, right? Because it's given by the y, so it's going to be minus the sine of alpha. Remember, the sine of alpha itself is always positive, so we have to put the plus or the minus. And cosine of theta, the cosine is positive in quadrant 4, so that's going to be the same as cosine of alpha. So once again, notice that in both of these cases, it is true that if you take absolute values just to ignore the signs, for simplicity, we get the same relationship. So how can we put all of these cases together into one single statement? We have been writing in here, okay? So what's the relationship between an angle and its reference angle when it comes to sine and cosine? Well, their values are exactly the same. What we just did was the proof of the following theorem. So we have the following. So theorem. So let theta be any angle. This is true for any angle theta. So let theta be any angle. And alpha be its reference angle. Okay, then what we just discussed was that if you do absolute value of the sine of theta, this will always give you the same thing as the absolute value, the sine of alpha. But actually, sine of alpha is always positive, so let me just even ignore the absolute value here. Okay, and if you do absolute value of cosine, so I'm putting the absolute value around the sine and cosine of theta because those are the ones that could be positive or negative, depending on the quadrant. But I don't need to put it around alpha because alpha is already in quadrant 1, so that's always positive. Okay, so this is what we just saw. So in other words, so i.e., if you want to know the sine of theta, well, this is going to be equal to plus or minus sine of alpha. If you remove the absolute value, then sine of theta is plus or minus sine of alpha. And similarly, cosine of theta is going to be given by plus or minus cosine of alpha. How do you know whether it's positive or negative? Well, it depends on the position, okay, of theta, where the plus or the minus is determined by the quadrant in which theta is. Is determined by the position of theta. So if theta is in quadrant 2, for example, sine is positive, so you pick the plus, and cosine is negative, so you pick the minus. Okay? And so on. In quadrant 3, they are both negative, so you pick the two minuses. And in quadrant 4, sine is negative and cosine is positive. So this is the easier way to remember this. Sine of an angle is the same, and cosine is the same as the reference angle up to a sine. You have to decide whether it's positive or negative depending on the quadrant. Okay, do you understand this? All right, so what's the moral of the story here? Now we're going to do some examples, but what's the moral of the story here? This means that when you want to calculate sine and cosine of an angle, you don't really have to worry about all the quadrants. All you really need to do is remember what happens in quadrant 1. Because once you have your answers for quadrant 1, then you can translate those answers to any other quadrant. Because any other angle, we have a reference angle back in quadrant 1. And you can then use that to find the sine and cosine. In particular, which we're going to do this later, once we do a couple more examples, you know, you probably have seen this around already, the unit circle, in which we have, there are some special angles, and you are required to know the sine, cosine, you know, all the trigonometric values for all of these angles that you see in this picture. So, first of all, the quadrantal angle 0, 90, 180, and 270 is very easy, right? Because you know exactly the points that corresponds to these angles, so you can figure out the sine and cosine easily. Okay, and then 60, 45, and 30. We already discussed this. This is what we did last time. The question is, what do you do about the other values, the other angles that we see here? Instead of memorizing this whole picture, our discussion right now says that if we know what happens here in quadrant 1, then you will know what happens in quadrant 2, quadrant 3, and quadrant 4. Because as you know, all of these, as you can notice, all of these other angles strategically They are in such a way so that the reference angles are one of the three basic angles that we have. Okay, so we're gonna come back once we do a couple more examples and using this reference angle business. We're gonna come back and we're gonna fill in this unit circle. Now we're gonna figure out the coordinates of all of these points, which means knowing the sine and the cosine of all of these angles. Okay. And my point is, you don't have to memorize the whole circle. All you have to do is remember what happens here in quadrant 1. And then you use your knowledge to extrapolate those results to the other quadrants. Okay, so let's first go back and let's do a couple more examples. Okay, so now since we already know values for some of the basic angles, then let's go ahead and let's find other angles without using calculator. Of course, the whole point here is doing these things without a calculator. Okay. So you're gonna need that skill if you are hoping to solve equations. So when we do trigonometric equations, you will need to know this, how to figure out these values quickly. All right, so example, find the values without calculator. Of course, I'm gonna give you some angles that you will be able to find. There are some that you cannot, that you have to use a calculator. But whenever we can avoid it, we will. All right, so part A, let's do cosine of 150. And B, let's do sine of 150. Let's see, C, let's do cosine 5 pi over 4. And then if we do that, then we should do also sine 5 pi over 4. Okay, let's do this 4 and then we're gonna do a couple more. Okay, but let's first do this 4. So I'm gonna do the 150 and then I'm gonna let you do the one with the 5 pi over 4. Okay, so again, this is this cosine of 150. This is an angle, and in what quadrant is this angle? We first need to focus ourselves in what quadrant this is. In what quadrant is 150? It's in quadrant 2. So we're gonna do this by reducing this to its reference angle, right? So let's figure out the reference angle. What's the reference angle of 150? It's gonna be alpha. So how do you find the reference angle? We are in quadrant 2, so we need to use the corresponding reduction formula. So what is it? It's 180 minus the angle, right? So remember, if you don't remember the formula, draw the picture, okay? Draw the little picture here. So you have 150 right here. The reference angle is this guy. So you should see that if you add the two angles, you get 180. So that's what tells you that formula that I just used. 180 minus 150 is alpha. Does everybody follow this? Okay, so alpha is equal to 30 degrees. That's the reference angle. So what is cosine of 150 according to our discussion? Because it's negative in quadrant 2, the cosine is negative. This is going to be the same thing as minus cosine of the reference angle, which is 30 degrees. And what do we know about cosine of 30? This is one of the special angles. This is square root of 2 over 2, and negative, because, cosine of 30 is square root of 3 over 2. And negative, because we are in quadrant 2. Okay, questions? All right, so similarly, we already found the reference angle, so now we have the job done here. So sine of 150 is going to be the same as sine of its angle. So let's see, plus or minus sine of 30. We need to decide which one do we pick. Do we pick the plus or the minus? How do we know? Which one do we pick here? You need to focus on the quadrant. On what quadrant is 150? It's in quadrant 2. What do you know about sine in quadrant 2? It's positive. Therefore, we pick the plus. So it's going to be positive sine of 30, and this is 1/2. That's the sine and cosine of 150. Questions? Right? So how about 5 pi over 4? What's the cosine of 5 pi over 4? First, let's figure out in what quadrant it is. Can anybody tell me what quadrant is 5 pi over 4? What quadrant is this guy? It's in quadrant 3. Very good. So because it's in quadrant 3, then we have a formula for alpha. How do we figure out alpha? The reference angle. What's the reduction formula for quadrant 3? Subtracting pi. Very good. So remember, you have two options, okay? You either memorize the formulas or think about it. You draw the little picture and then you will always see the formula right there. But it would be in quadrant 3, the formula is the angle minus pi. So 5 pi over 4 minus pi. So you subtract 180. Okay? So in this case, this is going to be pi over 4. Remember, pi over 4 is the same thing as 45 degrees. Okay? All right, so that means that cosine of 5 pi over 4 is going to be plus or minus cosine of pi over 4. Now we need to decide which one we pick. Should we pick the plus or the minus? So, are you sure? Yes, you're sure. So we are in quadrant 3, right? So it's going to be negative. Cosine is negative in quadrant 3. And what's cosine of pi over 4? That's square root of 2 over 2. Questions? Okay. Now, similarly, we already know the reference angle here. So sine of 5 pi over 4 is going to be minus the sine of pi over 4 because quadrant 3. The sine is negative. And so this is also negative square root of 2 over 2. Okay. All right. So let's see. How about 315? Cosine of 315, and therefore sine of 315. So go ahead and do this. Do this on your own. I'm going to give you 2 minutes to answer E and F. Time, I'm going to try another question. Okay, let's see. Anybody has an answer for E? What do we get for E? What quadrant is the angle? So we are in quadrant 4. So we need to look for the reference angle. What's the reference angle? What's alpha? 45 degrees, very good. So remember, in quadrant 4, what's the reduction formula? Do 360 minus your angle, 45 degrees. So cosine of 315 is going to be the same as, so remember, we have plus or minus cosine of 45. Which one do we pick, the positive or the negative? We pick the positive because we are in quadrant 4 and cosine is positive in quadrant 4. So this is square root of 2 over 2. Good. Now that we need this, now that we did this, then we can figure out the other one very easily. In quadrant 4, the sign is negative. So this is minus sine of 45. So this would be minus square root of 2 over 2. Questions? Okay, perfect. So hopefully you realize that then, if you want to know the sine or cosine of an angle, it's enough to just understand what's happening to the reference angle. If you know the values of the reference, of the sine and cosine of the reference angle, then you can then translate it and decide whether your answer will be plus or minus, right? All different, depending on the position. That's the whole point. All right. Let us now change the question a little bit. Here is another question. It's similar to what we're doing, but the way it's being asked is different. So, find an angle theta between 0 and 360, okay, such that, and then I'm giving you the condition. Let's see, in part A, I want you to find an angle so that when you find the sine of this angle is the same as the sine of 210. Of course, telling me theta equals 210 doesn't count, right? Because you have to give me something different. So find an angle whose sine is the same as the sine of 210. And the angle has to be between 60. Because if I don't put that restriction, you can just find any coterminal to 210 and that would do the job. But here this is not coterminal because I wanted to be between 0 and 360. So let's see, how would you go about in answering this question? What do you think is the first thing that we should do? Very good, sir. So we should figure out in what quadrant this angle should be. Can you tell me what quadrant this angle should be? So okay, wait. So what angle are you referring to? You talking about theta or are you talking about 210? Okay, yeah, 210 is in quadrant 3, yes. But remember, we're interested in theta. So what do we do here? And what quadrant is theta? This is the one that we really need to know. Are you sure? Let's see. Again, here you have to think about these things. So what do you know about sine of 210? Is it positive or negative? It's negative. Therefore, the theta that you need to give me, it has to have sign negative as well, right? Because otherwise they would not be equal to each other, the signs. So what other quadrant do you know the sign is negative? Quadrant 4. Do you understand this? So the angle that we're looking for, it has to be in quadrant 4. Does this make sense? So let's write this down. So the first thing is you need to figure out in what quadrant is the angle that you're looking for. So we know that sine of 210 is negative. Whatever it is, you can probably figure out what it is. Even if you don't really need to calculate this, you're just analyzing this. So this is a negative number, and so we know that sine of theta must be negative as well. But this only leaves you with one choice. So this means then that theta has to be in quadrant 4. Because quadrant 3 is already taken by 210. So you either do the analysis this way or you can draw the little picture, right? Because 210 somewhere in here. This is 210. So let's put our unit circle right here. This is the point. This point right here is the one that gives you, and the y value of this point is the one that gives you sine of 210, which is negative. What other point on the unit circle do you know that has the same y value? Because that's what it means to have the same sign. Well, go here. This is the other point on the unit circle that has the same sign y value. So this point, whatever that is, whatever this q is the one that is going to give you the angle that we're looking for. Do you guys understand this? Let me do this more nicely. So this is 1, negative 1, 1, negative 1. So right here, we have our angle 210. Right with this. This is the terminal side of 210. And the one that we're looking for is this one right here. This is theta. So from the picture, how do we know that theta is in quadrant 4? Because you have to figure out on this unit circle, you have the same sign. What we're really asking is what other point, given P, what other point on the circle has the same Y as P? There's only one answer, right? That's the Q that we just draw. So that's how you can see graphically that the answer must be in quadrant 4. You understand this? So I'm giving you two ways of realizing this conclusion that theta must be in quadrant 4. You either analyze it by remembering the sign, that is where is positive, where is negative, or you draw a little picture and it will tell you. Are you okay with this? Do you guys understand this? Yes or no? Okay, so then our question is, who is this guy? Well, if you look at the picture, since they have the same sign, what do we know? What does it mean to have the same sign? And they better have the same reference angle, right? Because the sine of theta is the same as minus the sine of its reference angle, and the same thing for 210. So we can see that they both have the same reference angle. So if they have the same sine value, that means that theta and 210 have the same reference angle. The same reference angle, alpha. So that's the conclusion that we can draw from here. If their sine values are to be the same, it's because then they have to have the same reference angle. Because after all, sine of theta equals minus sine of alpha, and sine of 210 equals minus sine of its reference angle. Therefore, the two guys are going to be equal to each other. Okay? Because they are both on quadrant 1, so there's only one option there. Okay, so having said that, then it should be clear how to proceed from here. Since they have the same reference angle, then we're going to use 210 to find it. So what's alpha? So alpha is going to be 210. Because 210 is in quadrant 3, all we have to do is take away from it 180. So this is going to give us 30 degrees. Now that we found the reference angle, which is 30 degrees, then we can use it to figure out theta. Theta is the angle that we're looking for in quadrant 4. All you have to do is use the reduction formula now. So what's the relationship between theta and alpha in quadrant 4? Looking at the picture, if you add them, what do we get? We get 360 because that completes the full revolution. So this is going to be 360 minus alpha. So theta is 360 minus 30, and this is going to be 330 degrees. So what angle do we know whose sine is the same as sine of 210? 310. Questions? this example. Okay, if there are no questions, then go ahead and do B. Find an angle theta whose cosine is the same as cosine of 115. And I give you 2 minutes to do. Okay, anybody has an answer for theta? This is something that you can do really quick. Once you understand the idea, this is something that is done very quickly. What's the first thing that we need to do? We need to figure out the quadrant of theta, right? For that, you can either draw the picture or use what you know about the sine. So let's see. What do we know about cosine of theta? It's the same thing as cosine of 115, and 115 is in quadrant 2, so this is negative. Cosine is negative in quadrant 2. So what does this tell you about theta? In what quadrant it is? Where else do you know that cosine is negative? Where is cosine negative? In quadrant 2, and where else? In quadrant 3. So this means that theta is in quadrant 3. Next, you can find the reference angle, right? Because the two cosines are equal, that means they have the same reference angle. So remember, reference angle of theta is the same as 115. So as reference angle of 115. So let's find it. So what's the reference angle of 115? How you find it? It's in quadrant 2, so you do 180 minus 115. Very good. So you get 65. So if the reference angle is 65, how do you find theta? We know that theta is in quadrant 3. What's the reduction formula? If you do 180 plus reference angle, you get theta. Remember the picture. This is theta, and this right here is your reference angle. So if you do 180, this part right here, plus alpha, you get theta. Okay? So this will be 180 plus 65. So what's the angle? 245. Questions? You guys understand this? Okay, perfect. And then let's do another type of example. This is slightly different than what we just did. See number 3. How about the following? So let us work now with a circle that's not the unit circle. So a circle with another radius. So find the point on a circle of radius 15 corresponding. I think you have a homework question similar to this. Corresponding to an angle of 35 degrees. And let's round to 3 decimal places. In other words, we should be using calculators for this. Round to 3 decimal places. Okay, so let's see, solution. Let's do this together. What's going on here? So we have, first of all, we have a big circle, right? We have a circle of radius 15. So let's put this circle. Here we have a circle with radius 15. And let's put out x and y. Okay, interesting. So here is x, here is y, and then this is going to be radius 15. So that's 15, 15, negative 15, negative 15. And then the question is find a point on a circle of radius 15 corresponding to the angle of 35 degrees. So if we do 35 degrees, and look something like this. If we draw this angle right here, 35 degrees, as you know, this is going to give you, this right here is 35. It's going to give you a point on the circle. Let's call it P. And the question really is what's x and what is y. Okay? So what we want to figure out here is the value of x and the value of y. Everybody understand the question? This is the setup of what's happening. Okay, so how do we do this? How do we figure this out? Well, of course, the idea is that we should try to relate this with what we already know about sine and cosine. But where we define sine and cosine, this is using the unit circle, circle with radius 1, and that's not what's going on here. So here is what we can do. Let's actually go ahead and let's draw the unit circle. So say this is 1, this is 1, then just put 1 here, negative 1, negative 1. Let's draw a unit circle. Okay, so when we draw the unit circle, then of course the same angle, 35, is gonna give us a point, right? Let's call that point, let's call it P prime. It's gonna give us a point on the unit circle, and we know the coordinates of P prime, right here. So what are the coordinates of P prime? The x value of P prime is gonna be cosine of 35, and the y value of P prime is gonna be the sine of 35. That's by definition. Everybody with this? All right. So now we're gonna do again a little bit more of high school geometry if you want. Okay. All right. So here is what's gonna happen. So I'm gonna first look at this big triangle. So I'm gonna drop a perpendicular here. So and then there is a big triangle involved, and then I'm gonna do the same thing here inside the blue circle. Okay. And then drop a perpendicular, and then there is a small little triangle. I want you to focus on that picture. In other words, let me zoom out and get out the extra stuff. So what we're focusing on right now is the following. So from here we get the following picture. So we get this. We're gonna have a big triangle. Okay. We're gonna have a big triangle, and then we have here small triangle given by the blue circle. They both have the same angle in common, namely 35 degrees. This is 90 degrees here. Okay, and this side right here equals y, because that's the y value of p. That's the big triangle, and then all of this equals x. And then in the small triangle, we have xp prime. So this little piece right here is p prime, and then this one right here is yp prime. This xp prime, as you know, is cosine of 35, and yp prime is sine of 35. So do you understand this? So I just took the triangle that we have inside the picture and put it outside without all the noise of the circle and so on. Okay? And moreover, this side right here is equal to 1, this piece right here, because that's the radius of the unit circle. And we also know the big side, this big hypotenuse, this is 15. That's the radius of the big circle. Are you okay with this so far? With this picture? Okay, so now the question is, with the information that we have, we need to be able to figure out what's x and what is y. Does this shape rings the bell? Do you remember seeing this back when you were in high school? Something like this. Something in geometry that we can use for this is the notion of similar triangles. Okay, so remember, whenever you're given two triangles, you can ask whether they are equal or not. We already kind of talked about that. And then something else that we could ask is, okay, maybe the triangles are not equal, but they could be similar. What do we mean by triangles being similar? Two triangles are similar if they have the same angles. Maybe the sides are not the same, but if the angles are the same, we say the triangles are similar. And in this case, it happens, right? Because the big and the small triangle, so we have a big and we have a small triangle right here. This big and the small triangle, they share an angle in common. They both have a 35-degree angle. They both have a 90-degree angle. So that means that this guy here is the same as this one. Okay? And you can even calculate what that is, because the sum of the interior angle is 180. So small triangle and the big triangle are similar. Small triangle and big triangle are similar, since all angles are the same. And then another property that similar triangles enjoy is, okay, all the angles are the same, but also the size of the triangles, they are proportional to each other. Okay? In other words, proportional means that when you look at the corresponding ratios, you will always get the same number. In other words, so this is what it means to be similar. The angles are the same and the sides are proportional. Okay? So small triangle and big triangle are similar since all angles are the same. Hence, the sides are proportional. And what that means is the following. For example, I can write the three sides of the small triangle. That would be xp prime, yp prime, and 1. Those are the three sides of the small triangle. And then if I divide each of these by the corresponding sides on the big triangle, those ratios are the same. That's what it means to be proportional. Okay? So how do you know what are the sides that correspond to each other? Well, the ones that oppose to the same angle. For example, xp prime corresponds to, opposes in the small triangle, the angle that we have on top with the two little lines. So on the big triangle, we have the angle with the two little lines. Which one opposes that one? That would be x. So xp prime corresponds to x. Yp prime, that's the one that opposes 35. So on the big triangle, corresponds to y. And then the hypotenuse of the small triangle corresponds to the hypotenuse of the big triangle, because they oppose the 90 degree. So 1 corresponds to 15. Okay? And similarity says that if you look at any of these ratios, they are equal to each other. Okay? This is what you get when you have similar triangles. In particular, we can now take advantage of this. For example, if you want to know what is x, we can say that xp prime over x equals 1 over 15 by looking at the first and the last expression in this equality, change of equalities that we have. So from here it follows that x is going to be 15 times xp prime, or 15 times cosine of 35. Remember, xp prime was cosine of 35. Right? So x is 15 cosine of 35, which we can approximate. So this will be exact value. And if you want, you can approximate to. So practice using your calculator. So make sure that it's in degree mode. Notice that we have degrees. So 35 hit cosine times 15. So this is about 12.287. Okay. And then if you want to know what is y, then we can use the middle with the last term. So y p prime over y equals 1 over 15. So y is going to be 15 times y p prime. That's 15 times sine of 35, because y of p prime is given by the sine. So that's the exact answer. If you want an approximation, then you calculate sine of 35 times 15. All right, questions? Decimal places, so we get 8.604. Questions on this? So I'm going to write the exact coordinates of P. Okay? So 15 times cosine of 35 and 15 times sine of 35. Did you guys understand this? Very good. Yes, so that's what I'm about to get to right now, Maria. But let me make sure that everybody understands this. Did you guys understand this? What we just did? So what's the, as Maria is pointing out, what's then the take on this? What's the takeaway from this example that we did? If you add on the unit circle, remember, every angle will always give you a point on any circle you want. Okay, because you can draw the picture that we just did. You have your circle, then you draw your angle, the terminal side will cross the circle. That point is going to have coordinates x, y. Now, if the circle that you have is the unit circle, then we know exactly what those coordinates are. Those are given by the cosine of the angle, that's the x, and the y is given by the sine of the angle. That's on the unit circle. But what if you have a circle that's not the unit circle, like this one, a circle with radius 15? How do we calculate the coordinates of the corresponding point? Well, what you can see here is that 15 is the radius. You can always play this business of similar triangles, and it will always come out to be x value is the radius times the cosine, the y value is the radius times the sine. In other words, just like in the unit circle, but we need to scale the coordinates of the point accordingly by the radius. So we are scaling by the radius. So note here r equals 15 is the radius of the circle. And so P is given by r times cosine of 35, r times sine of 35. And the point is that this is always the case, okay? So if you have a circle that's not the unit circle, and you want to know what's the point corresponding to a given angle, all you have to do is take the cosine and multiply by the radius, that's your x, take the sine and multiply by the radius, that's your y. And what's happening behind the scenes is what we just did. You can always play with this similar triangle business. Questions on this? That's a theorem, okay? So that's a theorem. So let theta be any angle. And let P be the point that theta defines on a circle. This time it's not on a unit circle, but on a circle of radius r. Then what we just saw is that we can find immediately the coordinates of the point. And P has coordinates r, comma, cosine of theta, r times cosine of theta, comma, r times sine of theta. Okay, that's what we just discussed. That you can now tell coordinates of the point on any circle if you know the angle that the point defines. Okay, so you have a circle, you pick a point, and it corresponds to a given angle. You could measure that angle, and then you can use this to figure out the coordinates of the point. Okay, so you can imagine how you may be using this in some applications, some little questions, and so on. Okay, so this is an extension, if you want, to the unit circle approach, because you know the unit circle is a special case in which r is equal to 1. If you put r equals 1, then you have cosine and sine for x and for y respectively. All right, questions? Okay, perfect. Okay, so then, as promised, let's go ahead and let's fill in the unit circle on our own. So, by the way, remember each of these angles they have their corresponding radian measure. In the homework, you have problems about this. I'm not going to worry about that. Remember, 30 degrees. Let's see, I'm gonna give some color coding here. Okay. So let's see. I'm gonna put here red, blue, and green. Okay, so 30 degrees is the same thing as pi over 6, 45 is pi over 4, and 60 is pi over 3. So let's see, let's go to quadrant 2. Which one of those three angles that we have in quadrant 2 has a reference angle of 30? So which one corresponds to 30? You can tell me. Which one has a reference angle of 30? Are you sure, Maria? It's gonna be 150. Okay, good. So I'm gonna put red in 150 just to signal in this picture that it corresponds to 30. Which one corresponds to, what's the reference angle of 135? It's 45. Good. And which one is the reference angle of 120? Very good. How about in quadrant 3? Which one is the reference angle of 210? Be 30. So in quadrant 3, it's easy to see. Notice that when the quadrants are opposite to each other, the reference angles actually, you can get it by just adding from quadrant 1 to quadrant 3, you add 180, right? So just draw a straight line, the one that's right opposed to it, that's the reference angle, okay? So what's the reference angle of 225? That's going to be the one that's right opposed to it. So that's 45. And what's the reference angle of 240? That's going to be 60. Now, in a similar way, quadrant 4, you can then match it with those of quadrant 2. So the quadrant 4 angles are going to have the same angle, the corresponding guys in quadrant 2. So that means this is green, this is blue, and this is red. And then you can verify that indeed reference angle of 330 is going to be 30, 350 is 45, and 360. Are you okay with this so far? All right. Now, let's figure out the sine and cosine of all of this. Let's fill in the unit circle. Now, let's see. First, let's do 0, 90, 180, and 270 because we know those. Remember, this is the unit circle. So this is equal to 1, this is 1, negative 1, negative 1. Okay? All right. So all we have to do is figure out the order pairs because that's going to give you sine and cosine, right? So for 0, this is 1, 0, right? For 90, this is 0, 1. Here we have negative 1, 0. And here we have 0, negative 1. So just by looking at those coordinates, you will know immediately what's the sine and what's the cosine of those angles, the quadrantal angles. Everybody okay with this? Okay, so now let us start filling in the circle. So for quadrant 1, here is where we need to work by memory. Quadrant 1, these are the special angles that we discussed last time, right? So for 30, here we need to put cosine, comma sine. So what's the cosine of 30? Square root of 3 over 2. And what's the sine of 30? That was 1/2. Okay? For 45 degrees, remember they are equal. And what were cosine and sine? Square root of 2 over 2. And they are equal to each other. Square root of 2 over 2, comma square root of 2 over 2. And finally, for 60, remember those are the values of 30 but flipped. So cosine of 60 is 1/2. The cosine of the sine of 60 is square root of 3 over 2. Okay with how we fill in quadrant 1. These were the values that we studied last time, that you are expected to know this. Like to memorize these values. Okay with this so far? All right. So now my claim to you is that with what we just discussed today, this is all you really need to know from the unit circle, because the other guys, you can get them from these values that we already have. There's no need to memorize that big picture, okay? As long as you know what's already on the screen, the information in quadrant 1, then that's it. You can recover what will happen in quadrant 2, 3, and 4. And this, of course, using reference angles, okay? So let's do it. Let's see. If we want to write down the coordinates of 120, so what's the reference angle of 120? And notice that the colors are helping. So what's the reference angle of 120? 60, right? So, I mean, you can answer very quickly, right? Because of the colors that I'm using. All right, so then what do we know? Remember, the sine and cosine of 120 is the same as the sine and cosine of 60, but up to a sign. Some of them could be positive, the other one is negative. We are in quadrant 2, so we know that cosine is negative, so it will be negative 1/2, and sine is positive, so square root of 3 over 2. Do you understand how I got this point? Do you understand this? Remember, the x value tells you cosine, and the y value tells you sine. It's basically the same that you have in quadrant 1, but then you need to decide one of them will be negative. Which one is it? In this case, it's the cosine, right? The picture also tells you is the x value, the negative one. Y's, yeah, the same, right? Okay. So how about for 135? So the reference angle is 45 degrees, and in this case, this would be minus square root of 2 over 2, comma square root of 2 over 2. And then for 150, the reference angle is 30. Cosine is negative here, so it's going to be negative square root of 2 over 2, comma 1/2. Questions about how we fill in quadrant 2? All right, so now let's do the same thing, quadrant 3. So 210, the reference angle is 30, right? Because it's a matching color. Now this time, what do we know about cosine and sine? They're both negative, right? So it's going to be negative square root of 3 over 2, comma negative 1/2. The coordinates of that point here is going to be 45, but both negative. And then 240, that corresponds to 60. So it's negative 1/2, comma negative square root of 3 over 2. And then finally, for quadrant 4, again, let's see, 300. That corresponds to 60, but this time x is positive and y is the negative 1. So that will be 1/2, comma negative square root of 3 over 2. And for 315, that's 45. X is positive, square root of 2 over 2, and y is negative. And then for 330, that corresponds to 30 degrees. X is positive, y is negative. So with this picture, you have the sine and the cosine of all of these angles. But my point to you is, instead of memorizing this picture that you find around online and so on, All you have to do is remember what happens in quadrant 1. Once you know that, you can immediately recover the rest. So there is no need to memorize this huge circle.